Here we go. Reaction mechanisms. Reaction mechanisms are actually fairly easy to grasp. It's like, hey, a reaction happens in steps. That's it. So like when you drive home, if you think about it, because you normally don't think about driving home, you just get in your car and you go. But really, like, let's pretend I lived, sure, let's pretend I lived in Perry, right by the theater. What's that place called? I heard like 10 things. Not Walker's, the farther one. Heritage, thank you. It seems like I've taught half the world to drive that lives there. So here's the Heritage Theater. All right, and I just live, here's Highway 89. You with me? And then way over here, not drawn to scale, obviously, is the high school. So let's say my drive consists of a few parts. I'm going to, here's 6 West. So I'm going to get on the parking lot, I'm going to go this way. And then I'm going to go over here to 5th West. And if you live over here and I describe a stupid route, get over it. I don't actually live there, but I'm not going to draw you a map to my house, even though most of you live, know where I live anyway. All right, then most likely, I don't know, to 1100 South. And so Walmart's right here, okay? And then you're going to take a left turn here. Then you're going to come here, okay? And then you're going to go here, and let's say you just live right behind it, okay? So your trip home technically consists of like 1, 2, 3, 4, 5 basic parts. Are you okay with that? Each one of those parts has its own specific rate, right? They all have different speed limits-ish. Okay, so 6 is 25, this road's 25, this is 30, this is 55. What's that? And this is like 45 for a millisecond, and then 50. No, no one does. Okay, I'll let the policemen know. All right, so they each have their own rate, right? But listen for a second. Does anyone sort of live there-ish? Okay, Willard. All right, well, this entire trip, the speed that you get home is sort of dominated by 1 or 2 main things. It's the lights. All right, it's mostly this stoplight right here, right? If you make that green left turn, this is the light I hate. If you get to this light right as it barely goes red, you might as well take a nap. You're going to be there forever, right? So my trip home from here to here, I mostly am concerned about this light and then maybe 1 or 2 of these on Main, but mostly that left turn light. You okay with that? Most of you that live in Perry, you're concerned about this light or that light going that way, correct? All right, Manaway kids, you're probably worried just about the light right up there. It's not really that stressful because that light's fast anyway. That light, I don't mind that light at all, personally. It's short, and it's going to save lives. Okay. All right, these stoplights in this reaction mechanism idea, they are going to have a name. They're going to be called the rate determining step. Factor's fine. So even today, I drove to school and there was It was me and my GMC truck, and then this guy in his Ford. And we were both stopped at a light. No. But he wanted to be in front of me, which was fine. So he sped up a lot faster and got in front of me to take a right to come down Forest Street. All right, which I didn't care. I really don't care. Driver's ed has killed all road rage. And I'm like, okay, you go, bro. Because like he floored it to get in front of me to take that right. That was fine. And then we both came to the same stop sign at the post office. You with me? And then once again, he wasted a ton of gas going down the hill. Because then he came to the light, the new light here on 5th. You with me? All right. And it was red for him. But I was so slow, by the time I got there, it went green. And then I went right past him because he was at 0 and I was at 35 because I wasn't in a hurry. All right? The light determined how fast we could get down that road, not the speed limit. You okay with that? All right. When we talk about this reaction mechanism, there is usually always something we call the rate determining step. The rate determining step will tell you how fast the reaction is going to happen. Now, we have done an activity where we talked about catalysts, but now will you think with your old lab partnership when we made widgets and talk about what was the rate determining step? For most groups, what was the rate determining step? Putting the staples in, right? But for some groups, that was not the rate determining step, correct? What was your rate determining step? Signatures, all right? Anyone else have something else they thought went slower? Yours? No, besides staplers or hole punches, sorry. Go ahead. What? Tearing the papers. All right, now listen. Those groups that had different rate determining steps had different tools, right? They had a different reaction mechanism. They went about doing it a different way. They didn't have to peel a single staple off at a time, find a way to shove it through 9 pieces of paper and then fold it. It was a different process, and so the slow step or the rate determining step was skipped. All right, here we go. Reactions may occur all at once or through several discrete steps. Each of these processes is known as an elementary reaction or elementary process. Okay? So you're going to end up with like a part A, a part B, and a part C. Individually, we would call these elementary processes. Okay? So the individual steps are the elementary processes. That would be like your ride home. You drove on 5th West. You drove on 5th South. You drove on 6th West. You drove on 11th South. You drove on 89 and you took a left. Okay? Now, the overall reaction will include some of the parts from the elementary reactions, but not all. Okay. The molecularity, this is kind of a new word. It's not like one we use a ton, but you do need to know this. The molecularity of a process. How many molecules are involved in the process? All right. We are going to mostly talk about unimolecular and bimolecular, but there are occasionally termolecular. Did I have you watch a video? I don't remember while I was gone. We did? All right. Got you. Maybe I'll put this out there tonight. You don't have to watch it, but there's a good video on this by Tyler DeWitt. All right. So if you've ever ridden a unicycle or seen a unicorn, what do they have in common? one thing. And they're both impossible. Unimolecular means one molecule is involved in a reaction. And if that happens, it's just breaking apart into its products. It's a decomposition reaction. Like carbonic acid. All right. Bimolecular. There are two options for bimolecular. The options are two of the same molecule collide to form the same product. That would be like a Cl reacting with a Cl to make Cl2. Okay? The other option for bimolecular are two different reactants reacting to form products like H and Cl combining to make HCl. Okay? Not that bad. Ter, you could have the same three things running into each other, or two of the same things and then a second thing that's different, or all three of the different things. Now, these are rare because in order for this to happen, all three have to run into each other at the same moment with the right amount of energy and the right orientation. And that's pretty hard. It's pretty easy to have one thing just fall apart. It's pretty easy to have two things collide. It's very difficult to have three things simultaneously collide. All right? Right. So carbon dioxide would be really rare, except for it happens in steps, where your O and your O are going to combine themselves, and then that combines with a carbon. So it's going to end up to be a two-step process. Yep. All right, now, the rate law for a unimolecular is rate equals K times A. Bimolecular is rate equals Ka squared or Ka times B. All right, because this thing will tell you the overall order of the reaction. The overall is when you add the exponents. So if there's only one thing, the exponent must be a 2. If there's two different things, each individual exponent must be a 1. If it's ter, it must be to the 3, or to the 2 and the 1, or the 1, 1, and 1. Okay? Molecularity will tell you what's happening here, and it will give you the rate law. Okay? It's not awful, but it's got to kind of practice with it. Yes? Well, sure, you could go forever if you want, but the likelihood of 4 things simultaneously running into each other at the exact same moment are super limited. And I just realized that sentence was redundant, but oh well. Okay. So a multi-step mechanism, that's what we've been talking about. In a multi-step process, one of the steps will be slower than all the others. The overall reaction cannot occur faster than its slowest rate-determining step. Okay? Now, we don't have toll booths here in Utah. I know where one is, in fact, is all. All right? Yep, in Ogden. But when I lived in Virginia or in Colorado, they fixed them now. In Colorado, they're all digital. No matter how fast you went down the turnpike, is what they call them, it was how fast you got through the plazas that really mattered. And so in this example, this is where the slow step would be. This one, there's not many people backed up, right? So no matter how fast Plaza B went, that'd be the toll booth, really we would worry about how fast Plaza A was, because that's the slow part. Okay? Now, you may be more familiar waiting in line at the airport. What's the number one thing you worry about at the airport? Is it the line to get onto the plane? No, it's security, right? It doesn't matter how fast they board the plane. Your rate at the airport is determined by security. Okay? So, I mean, lots of examples, not too bad. But in chemistry, there's usually a step that is slower than the others. And we will once again call that the rate determining step. All right. So this is my own handwriting, or typing, so it must be some sort of summary. So the order of the reaction can give you clues about the mechanism, and the mechanism can give you the order of the reaction. So if you have one, you can find the other either way. Okay? Now we'll go through this process. Some of you will actually like this. Some of you probably even like chapter 14. You're like, this is kind of nice. It's not hard math. So here we go. Consider the following mechanisms. And this is how things will be given to you very often. It says, find the slow step and eliminate any intermediates, and then take the reactants in and before the slow step, and that will be the rate law. So this isn't my finest sentence I've ever written, but this is the instructions on how you're going to do this process. So if you're a note taker, write that down. If you're a mental note taker, stare at that for a minute. All right, because we're going to do this process, and it's going to be pretty simple. It can be a little complicated depending on where the slow one is, but this will be very, very simple. So the first thing to do, find the slow step. The slow is labeled as the first one, right? What I would do is cross out anything you see after you read the word slow, because nothing matters after the slow step. It's like you wanted to eat chocolate chip cookies. You have to make them. The slow step is cooking them in the oven, right? So they're out of the oven and then you eat them. In short, it takes you 30 seconds to eat a cookie, right? But that's not what you're worried about. You're worried about the 12 minutes you had to cook them. The flour you had to put in, the eggs you had to the mixing. All the crap before is what determined how fast you ate a cookie, not how fast you ate the cookie. You with me? So we get rid of everything after the slow. Then, all right, eliminate any intermediates. In this problem, there are not any intermediates that we're going to care about. But for a second, look. An intermediate in this problem would be something that is produced in one reaction and consumed in the next reaction or a later reaction. That's what an intermediate is. Now, this one we don't care because we don't care about anything after the slow step. Are you okay with that? But that's what an intermediate would be. Something on both sides of the arrow that's exactly the same. Okay, so we've found it. We've eliminated any intermediates. Then take the reactants. So notice this word. That means I'm not going to worry about these things either. Take the reactants in and before the slow step. Well, this one was the first one, so it doesn't really matter. And that will be the rate law. So I take A2. And how many are there represented here? Just one, right? If there was another, there'd be a number. All right, so it's raised to the first. And B2, and there's not another one of those, so it would be B2 to the first. Then I would just say my rate is equal to K times that to the first and that to the first. And I could say a few things vocabulary-wise. I could say the overall reaction is second order. Or I could say the overall reaction is bimolecular. I could also say it is unimolecular based on A and unimolecular based on B. Fair enough? Okay. Let's do one that's going to be harder here. All right. This is your slow step now. So we're going to follow the same ideas. See if you can do it yourself real quick. Since the second one is a slow step, there's nothing after it to eliminate. Okay? So the next step is to find any intermediates. The only intermediate is the oxygen there and the oxygen there. It's created in one, meaning it's a product, and it's a reactant in another, so I can eliminate it. All right. Then I don't care about products. I just care about my reactants. Are we okay with that? So my rate will be equal to KO3, and there are 2 of them represented here left. So it is to the second power. We okay with that? So we find the slow step. We eliminate intermediates. Then we take the only reactants that are left and we put those into our rate law. If something is represented more than once, then you write how many times it's represented as its exponent. Did someone say, did you say something? Hold on. I definitely am going deaf. What's that? Right. Good point. So you can only eliminate the fast if it is after the slow. We worry about where the slow step is and anything before it, but nothing after it. Is that all right? Yeah, I think I got a handful of them. Okay, give this one a shot. Okay, so not bad. First thing I can do, I can just eliminate this because I can eliminate anything after the slow step. Then I can eliminate these because I care about the reactants. So then anything I have left comes into the rate law. So the rate will be equal to K times O3 and NO. Neither of them are represented more than once. That's an ugly 3, but it is a 3. So they're both to the first power. Okay? Now, post, let's pretend, and everyone actually, let's pretend that we switch this around and we'll say this one is slow and this is fast. Try that. So if we flip this around, we cannot cross out the top because it is before the slow step. So the next thing I would do is to eliminate intermediates, and NO2 is the only intermediate, correct? Oh, I didn't even look right there. NO is right there and right there. Okay, that's a 2. All right, it's a product both sides. So it's not considered an intermediate. But for my rate law, it's not going to matter because then I get rid of products because I care about reactants, correct? So I'm left with the rate equals K, O3, and O. And that would be it. You okay with that, Caitlin? Okay. All right. Now, this is a typical way to see it. It's confusing, so make sure you're looking for a second. This is showing you the overall reaction. And then it's saying it happened in these 2 steps. Are you all right with that? These are just saying that you have one K and the second K, but don't worry about those. So when you do this and it's given to you this way, you are not canceling anything out of the top. You're looking at these 2. Is that okay? Okay, try that. Should be easy because slow's first. Like, it's very easy. Whoops. Oh, hey, that's a pretty good R for a line tool. All right. Rate equals K NO2Cl to the first. Okay. No, it's not to the second, because remember, if it's after the slow step, I don't care about it at all. Okay? Okay, this is another similar one. This is your overall reaction here. So you do not eliminate things based on that. It's just saying, hey, this reaction happened in these two steps. Is this the same one? No, but it's boring because slow's first again. But whatever. How do we feel about this idea so far? Good? Okay. I'll just skip on here. Here. Same idea. Here's your overall. Here are your two reactions. The second one is slow. See if you can write that out, and then we'll call this good. The easiest free response on this test coming up is one of these. Very simple. This is your slow step. So we can eliminate the two I intermediates. You all right with that? Anything else eliminated? All right, rate equals K times I2 and H2. Both to the first. We don't care about HI because it's a product. Okay. So here is one. This is off an AP test. I don't know. It's within the last 5 years. So this is exactly like you'll see one on the test. So you are given this data table. In this data table, I'm giving you the initial concentrations of the two reactants and then the rate. So which process do we use to find the rate law with that data table? The first one we taught you. The ones with lists, correct? So you would plug that in. Then you can determine the overall reactions. You can calculate K. You can find the concentration when exactly 1/2 of the original amount of H2 had been consumed. That sounds like half-life. All right. You can describe the appearance of nitrogen to the disappearance of hydrogen. That might seem tricky, but this one real quick. Nitrogen gas is right here. It appears with a 1. This disappears with a 2. So nitrogen appears at 1/2 the rate hydrogen disappears. Does that make sense? And then it says the following sequence of elementary steps is proposed mechanism for the reaction. Based on the data presented, which of the above is the rate determining step? And explain your reasoning. All right, this is pretty cool. This stuff, will tell you the rate law, right? Well, the rate law will tell you which one of these is fast and slow. Because once you've gotten so that each part of your rate law is represented, then you've hit your slow step. Does that kind of make any sense at all? So your rate law will tell you each part of reactants that will have gone into this reaction. So why don't we take the rest of the hour and try and work on this problem?